Hello, my name is Todd Giddings, and in this presentation I'm going to explain how groundwater is a very efficient source of energy for building heating and cooling. This case history is located in Center County, and the well supplying the groundwater is on the Ordovician Nittany Dolomite Formation. This case history is about my 10,000 square foot office building heating and cooling system, and it's located in State College, where the winter temperatures require 5,639 heating degree days. My building was constructed in 1986, and it has 5 heating, ventilating, and air conditioning zones. The supply well is drilled into the Nittany Dolomite Formation, and it supplies groundwater to 5 open-loop 2-speed geothermal heat pump units. In 2013, I replaced all the bulbs with T8 efficient bulbs, and I added LED lighting as an upgrade. And then in 2016, I installed a 25 kilowatt photovoltaic solar system with the panels sitting on the building roof. Here's a picture of the building, and it's showing that it has 2 floors for the 10,000 square feet of area, and there are the degree days of heating demand in winter. This transformer supplies 3-phase 208 volt power to the building. And there is the casing of the supply well that's drilled into the Nittany Formation, and the well has a yield of greater than 50 gallons per minute. On the windward side of the building, the walls are 8 inches thick for additional insulation, and there are solar overhangs on both sides of the building. All the other walls are 6-inch thick side walls and the end wall at the rear. Back in 2015, before the photovoltaic system came online, my heating and cooling cost was 56 cents per square foot of the building per year. And this compares to other 10,000 square foot office buildings in State College, where the heating and cooling costs are $2 or $2.50. Here are the 6-inch walls, and here is the solar overhang, and you can see that the solar overhang shades the windows. The windows have double panes, again to provide additional insulation. This aerial view of the office park shows my building in the red rectangle, and out in the front yard at the circle is the groundwater supply well. The discharge of water from the geothermal heat pumps in the building flows through storm drains and then exits into a drainage ditch leading to a stormwater detention basin. The wiggly arrow shows the area of open drainage ditch where groundwater infiltration occurs. And this recharge to the Nittany Dolomite Formation is located 700 feet from the water supply well, which is important so that the warmer or cooler water in summer or winter doesn't recirculate directly back to the supply well. Surface flow in the drainage ditch is shown by the blue arrow, and in the red ellipse there is an area of infiltration to groundwater where the return from the geothermal heat pumps makes its way down through the soil and into the Nittany Dolomite Formation. Geothermal energy is from solar energy. And here in this diagram, the sunlight is absorbed or reflected or absorbed or reflected. And importantly, 51% of the solar energy is absorbed by the ground each year. So the Earth is like a solar battery, absorbing over half of the sun's energy, and the ground stays at a relatively constant temperature throughout the seasons, providing a warm source in winter and a cool heat sink in summer. So it's important to note that this is renewable energy in the ground that is provided by the sunlight. And this type of geothermal energy is not the hot rock geothermal energy from the molten core of the earth, such as the heat that provides the source for Old Faithful geyser. Pennsylvania groundwater temperatures are shown on this map, and they vary from about 48 degrees at the New York border down to the Maryland and West Virginia border, where the temperatures are 52 or 53 degrees. And here in State College, where my supply well is located, the groundwater temperature is 51 degrees Fahrenheit. So why is a geothermal heat pump so efficient? In heating the building, by buying 1 kilowatt hour of electric energy to run the heat pumps, they extract out of the 51 degree groundwater 4.1 kilowatt hours of renewable energy. And the electric energy coming in to run the equipment doing work is converted to heat. So there are 5.1 kilowatt hours of energy entering the building, and you paid for 1 kilowatt hour of energy, and that yields a coefficient of performance or efficiency of 5.1. The 51 degree groundwater entering the heat pump in heating the building is cooled down to 41 degrees, which is recharged back into the aquifer to again return to its 51 degree Fahrenheit temperature. A compressor in the geothermal heat pump uses a refrigerant to absorb energy from the groundwater. And that refrigerant to groundwater heat exchanger has an entering refrigerant temperature of about 0 degrees Fahrenheit. And then the compressor compresses the refrigerant and raises its temperature, and through a heat exchanger supplies hot air heat at 105 degrees Fahrenheit in order to heat the building on the coldest days of winter. So the key is the heat exchangers and the compressor that raises the temperature of the refrigerant. When you're cooling the building, you need to reject 10 kilowatt hours of energy into the groundwater. So you buy 1 kilowatt hour of energy to run the geothermal heat pumps, and they reject 72 degree Fahrenheit groundwater into the Nittany Dolomite aquifer, where it returns to 51 degrees Fahrenheit. So 10 kilowatt hours of energy into the earth by paying for one gives a coefficient of performance or efficiency of 10. The supply water directly from the supply well is 51 degrees Fahrenheit. And that 21 degree temperature difference is achieved by the compressor again, where a heat exchanger takes the groundwater and puts the heat into it from the refrigerant, raising it from 51 to 72 degrees. The compressor has created that temperature difference by compression, and the heat is absorbed from an air to refrigerant heat exchanger, which discharges a dehumidified or dry 60 degree Fahrenheit cool air into the building. Looking at the monthly kilowatt hours of electric energy used, that's shown on the y-axis, and the months are on the x-axis. So the blue shows the kilowatt hours used, and you notice that when you draw a curve across the top of the bars, there's a summer peak due to the air conditioning effort in July and August, and you have a reduced kilowatt hours used when the outdoor temperature is ideal in May and June and in September and October. Superimposing the kilowatt hours paid for, you can see that they're significantly less than the kilowatt hours used. So the difference between the blue curve and the red curve is the energy provided by the photovoltaic solar system. Here in this graph, I'm comparing building heating methods. And the y-axis shows the coefficient of performance. red equals energy purchased, and blue equals energy transferred. So fuel oil can achieve in a very modern high efficiency furnace about 90%, just below a coefficient of performance of 1. Modern gas furnaces can get up to maybe 98%. And then direct electric heat has a coefficient of performance of 1. Air source heat pumps have a coefficient of performance of almost 3, and the blue part of the bar graph shows the energy transferred from or into the outside air around the building by the heat pump. A ground source geothermal heat pump will achieve a coefficient of performance of just over 4, and it's transferring a lot of heat into and out of the ground. And then finally we come to my water source geothermal heat pump system, which has a coefficient of performance of 5.1. So it's transferring 4.1 units of heat into or out of the groundwater while paying for only 1 unit. And then the benefit of the photovoltaic solar system reduces the cost of the purchased energy. So the area in the red ellipse illustrates in the blue part of the bars the heat transfer into or out of the air or the earth or the groundwater. And this is how decarbonization is achieved using these types of systems. Thank you.